All right, let's get going. Great, thanks. Okay, let's get started. So, hello again. Let's see, we're drawing to the end of the semester now, right? So, this is how far we've gotten. We've got just 3 more lectures left, 3 more practicals, and then a final class. Oops. I have not turned on my microphone. Okay, so yes, we're almost finished with the semester. 3 more weeks of regular classes, and then the one final class on the last day of classes on May 2nd. Sorry. And so now we're sort of moving into some other sort of assorted topics, including some work, some things that I've worked on at various points, which gives us things to play with. So we have the current mini project 3, which is due not this Wednesday, but the Wednesday after. And then we have the final projects, which I hope you're all set for at the moment. Normally I have the final project reports due a week after the end of the semester, a week after the final class. I hope that'll work. For those of you who... Are you graduating this semester? Yeah. So then it might get a little tight for people who have to get grades in. But I'll make sure we do it as long as I forget what there's a deadline. But that should be okay. If I have it like by May 9th, it should be okay, I think. I'll let you know if there's any problem with that. In terms of what to put in the what to aim for in the projects, the things I'm looking for are some evidence that you've picked up some material from the class, so something about using the techniques or the ideas that we've covered in the class. And then more generally, what I'm looking for is a project that is sort of done in a professional and systematic engineering way. And what I mean by that is, and this is a little interesting because in some of the projects you're doing have this kind of musical aspect, which is not really an engineering criterion. But that's okay. What I am looking for is if you can start with some musical goal, like you want to produce a particular kind of sound, and then that's kind of maybe a little hard to pin down. But then you sort of say, okay, well, the way I'm going to translate that into some engineering goal is I want to produce sounds with these properties under these conditions, things like this. And then okay, so now we're into engineering. You've got a goal here. Then you talk about how you're going to implement that. So I'm going to do this, 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 and this. And then you do it, and then you try it, and then you sort of have that. There needs to be some kind of assessment of what happened, right? So it's what doesn't work well for me is if you just say, oh, we try this, and we put it together, and look at this, but there's no effort to actually analyze what's going on. So hopefully when you've defined what you want to do in a more concrete sense, you can then analyze, well, did it do this, this, and this like I wanted it to? Did it produce a distribution of energy with different characteristics, something like this? Now, there's a step beyond that, which is like, did it meet my musical goals, if that's what I'm doing? Did it sound nice? That's harder to assess. And that's okay if you don't do that. You can just, say, and I think it sounded nice, or and I don't think it sounded nice. But I do want there to be some level of analysis where you just look at the signals coming out of whatever you do and assess whether it, achieved the goals that you were trying to achieve. And then ideally, I mean, I don't know about ideally, but often it won't meet those goals, and that gives you an opportunity to display your engineering skill again, which is to say, okay, well, here's what happened. This is not quite what I intended. And then, oh, okay, that makes sense because here's why there was a difference between what I intended and what I specified. And here's a way I could possibly improve that. And then hopefully if you have the time, you've got the scope to go back and try a second version and see if you can improve it. So that's the kind of thing that's what I'm looking for. A specification, an implementation, an assessment, and then hopefully a second iteration trying to improve the implementation. That's kind of like, that checks all the boxes for me. The point about this is that what I'm looking for is not particularly success, right? So it's okay to start off with a very ambitious goal and then sort of not achieve it, as long as you are able to do a series of these, what you can say what you're trying to do, the sub-goals, and then you do a good job of analyzing how well you met the sub-goal, right? So achievement is really kind of, it's nice, but it's secondary. What's important is the way that you approach and assess the individual sub-goals that you specify. And to some extent, the way that you analyze a problem into sub-goals. That's also good engineering design. But it's not, if you feel like, oh man, I tried really hard, I tried all these things and nothing worked, that's not a problem in itself, right? If you tried them, if they were sensible things to try and you did a good job of trying them and you were able to say something interesting about why they didn't work, then I'm totally happy. Okay? Any questions about the final project or anything else? Okay. So today we're talking about, it says here, audio alignment and cover songs, but a range of topics to do with matching things together, matching music, audio things together. So it's because of the nature of musical data, there are often cases where we have different pieces of data which are about the same piece of music. And the thing, one of the kind of defining aspects of music is it has this time axis. And so we can have these different representations of the music, and we can think about trying to align them on the time axis. So, for instance, we might have different performances of the same piece of music, in which case, they had slightly different tempos or whatever, so they wouldn't naturally align in time, but we'd like to be able to find the point, the note, the point in the music in one piece that exactly aligns with some point in the other piece. Or we might have different representations of the notes. So we might have the notes. We might have the actual recording of the audio, and we might have some kind of symbolic description like the score. So that's what's shown here, and this is the work of Meinhard Müller and some various collaborators. And what they did was they had this kind of very nice, very attractive application where it has a picture of the score as if it were, a book, and then it highlights it has a piece of music, a recording, which is analyzed, and then as the recording is playing, it highlights the part of the score that corresponds to the current piece of music. So I was able to find a video on his website. I guess there was it was covered by German TV because he's in Germany. So the narration is in German, but hopefully you can sort of get the general idea of what's going on here. Let's just see if this works. I'm sorry that the contrast's not so good.
Untersucht Musikhilfe von Computern. Hat ein Pilotprojekt mit der Musikhochschule des Saarlandes ins Leben gerufen. Die Informatik soll für die
So you can see the highlighting moving along in time to the music.
Also Musikdaten sind komplex. Musikdaten kann man auch ganz unterschiedlicherweise darstellen.
So that doesn't. It's not a particularly clear display, but it gives you the idea of what's going on. I wanted to show you the actual thing moving, just so that you get the idea of what it's doing. And of course, that's very nice. Yeah.
I guess I didn't quite understand. I understand when you talk about how much time access with the different performances of
Yeah.
the same piece, but I don't know what you mean by performances support.
Well, did you see? I don't know. Some of you can see in the video. This little box moves along, and there was a piano playing in the background, and the box is moving along, showing which notes the piano is playing.
That's just like a sort of aligning score with the performance.
Right. So what does that involve? We've got, I think, at least in one version of this project, they actually started off with the image of the page. Then they have the optical music recognition problem of taking this and figuring out what it means, what notes there are in that this is actually a human pianist can take this and turn it into a performance, and so this is a sufficient encoding of the actual notes. So figuring out the notes that are there, or they may have started with a separate representation that already had the notes in machine-readable form, and then listening to the audio and figuring out which part, how far which notes were playing based on the score, which is an alignment problem. But it's very nice because then if you're trying to listen to it and learn to read the music or whatever, you're kept in the right place. So what can we do with this? We can do this score display thing. We can actually synchronize different tracks by figuring out the time skew and then using timescale modification, the phase vocoder type things, to make them line up. And we can also use it, if we can do this thing of synchronizing a score to a piece of audio, we can then use this to sort of get post hoc transcriptions. That if I have a recording of someone playing the piano, and I want to be able to say exactly when each note occurs. If I have this pre-existing list of all the notes that they played, I can use that, I can align that, and I've got a pretty good transcript. And one of the reasons we're interested in that part is because we can then use that to train a classifier to do transcription. Right? That we can then I've suddenly got all these examples of audio, what the transcription output should be, which I was able to get because I knew what the notes should be. But then I can train a classifier just on those two cases, and then I can show it other recordings where I don't have the score, and it'll maybe figure out what the notes are, more or less. Okay. So one popular tool in working with these kinds of problems is the similarity matrix. And it's a pretty simple idea. We've got two sequences. And so in this case, it's the beat chroma matrices. So it's the beat synchronous chroma representations for two different versions of Let It Be, the Beatles and Nick Cave. And then for every frame in our analysis, we do a comparison of this single frame here with all of the frames over here. We have some distance measure, perhaps, some kind of way of comparing two in this case 12-dimensional vectors. So we can just take a Euclidean distance between them, and that's what we plot on this matrix. So if there are NA frames here and NB frames here, we get this NA times NB matrix of these distance values or similarity values. Euclidean distance, right, or the squared Euclidean distance is just the sum of the squares of the differences between the individual bins in the two vectors. Another popular thing to use is the normalized inner product, which is the cosine distance, which is the inner product divided by the geometric mean of what the inner product would be, what the norm of the two vectors, right? So this thing is always smaller than 1, or it's always has a magnitude smaller than 1. It can go negative because this thing can go negative. But it's actually the cosine, this part here is the cosine of the angle between these two vectors, unit vectors pointing in the direction of these two things in however dimensional space it is, 12-dimensional space. So when they're pointing in the same direction, when they're scaled versions of one another, it's 0. And when they're pointing in opposite directions, when they're negatives of one another, it's when they're pointing in the same direction, it's the cosine of the angle, so it's 1. When they're opposite directions, it's minus 1. So we take 1 minus that to get a distance such that it's 0 when they're pointing in the same direction, and it's got a maximum value of 2 when they're pointing in opposite directions. Just to sort of motivate the problem, here's the Nick Cave version of Let It Be. Just as a typical example of a cover version of a piece of music.
When I'm find myself in times of trouble, Mother Mary comes to me, speaking words of wisdom, let it be.
Okay, so it's, it's the same piece of music, but it's very different from the Beatles' original. Different instrumentation, right? He's using guitar rather than just piano. And his singing performance is different. He's sort of got a slightly different rhythm, slightly different melody. Now, it might be interesting to play that alongside the Beatles version. But if we just played them together at the same time, we get this. Maybe. So this is both versions together, I think. Oops, no. Sorry. Okay, so yes. The point is that they're not synchronized in time, so we play them together, we have two things playing together, but they're kind of unrelated and you can't hear what's going on at all. Okay. So how are we going to align them? Well, we're going to use our dynamic programming again. So let's just look at this again. I feel like I kind of didn't quite give the insight last time I spoke about this. The idea in dynamic programming is we've got this matrix like that distance matrix which compares every frame of each sequence with every frame of the other sequence. And so that might be this underlying matrix here of the grayscale values. That's just how similar frame 2 of sequence A is to each of the frames of sequence B. And so here we got, these are probably cosine distances, so they've got a largest value, or similarities of distances. They have a minimum value of 0, and in here the largest value is 1 for this scale. And what we're trying to do with dynamic programming is to find a path, a set of values for each axis, a set of steps. K index is the steps, and ij of k is the point, the kth step along the best path, such that we minimize the total cost. The sum of d, ij, ik, jk, which d is the local distance, the actual sort of the color of the square we step through, plus some transition cost, which talks about the preferability of a particular transition from step k-1 to step k. And so typically we'll use this to essentially eliminate many transitions, and then we can also use it to bias particular other transitions. So for this particular instance of the algorithm, there are 3 allowable transitions. I can get to ik, jk either by keeping j the same but advancing I, by keeping I the same but advancing j, or by advancing both of them. This is the classic dynamic programming transition matrix, but in fact you can have any kind of matrix like this, as long as you've got some kind of progress. You can't have something that loops back indefinitely. At least I don't know how that would work. No, you can't do that. Right? You have to be able to visit one step once and for all. But you can have things that always involve a forward step in time, but have maybe you can jump points on one axis, or you can have other things going on like that. But once you define this transition constraint and the penalty, so here we're saying we like these diagonal steps best, so we're going to give them a transition cost of 0. These horizontal and vertical steps, they're okay, but we're going to add a little bit of penalty, an extra cost of 0.1 every time we take one of those. Then we can find the best cost and implicitly the best path with this recursive calculation that for each point in the total cost matrix, C star, the best cost matrix, which tells you the best cost to every point ij. It's just the minimum of the local cost plus the minimum of the preceding costs over the allowable preceding points plus the corresponding penalties, right? So if I've calculated C star for all three of these points, and I'm trying to, which is the best cost by over all possible paths for any one of these points, I'm trying to find the best cost path to this point. I just have to say, well, whatever it is, I'm going to have to add in the cost of this local point here. But then it's going to be whatever the cost was up to the preceding point plus the transition cost. So I can calculate what this is plus 0.1, what the cost to here is plus 0, the cost to here is plus 0.1. Find whichever of those is smallest, and that's guaranteed. That's going to now give me the lowest possible cost I can get to this point here. Yeah. It's n times n, so it's the size of the matrix. Basically, it's Viterbi decoding is dynamic programming, right? Yeah. So Viterbi decoding, you don't have a constraint like this. You can transition from any point in this column to this point, but you have a transition matrix and you have a best cost, and so it's the same algorithm. Yeah, just different way of structuring the cost. And so this picture here is to sort of illustrate what's going on. Shows you the little numbers are the C stars, right? The best cost, the lowest cost over all paths to get to this point. And then the actual, because it's saying, well, for here, when I got to this point, I could have either done, so this point is like, has a local cost of like 0.2 or something. Around there, 0.25. I could have gone from this point and gone like this. I could have gone from this point and gone like this. Or I could have gone from this point and gone like this. So it turns out that although this, to one significant figure, this is 0.7 and 0.6, the cost from here would have been 0.7 plus 0. The cost from here would have been 0.6 plus 0.1, but it turns out, I guess, this was just a little bit smaller, so it actually preferred, maybe it's 0.59 plus 0.1. It preferred getting the cost from here. And so I guess the local cost here must be 0.3, because when we add them on, we get 1.0. When we want to actually find an alignment, so we calculate this for the entire matrix, right? We start here, then we do this one. Well, the only thing that's available is start from the cell down here and then all the way up. Then we do these ones, and so this one now we have a real choice, and etc. We can calculate all the costs like this, and we can always work it out. And then we end up with all this traceback information. When we get to the last cell here, we basically have to decide where we want to end, which is a little bit of there's some different variants of the algorithm where you can either always try and end in the last cell, or you can say I have to end on somewhere on the final edge. I have to finish one of the vectors, but not one of the sequences, but not necessarily get to the end of the other sequence. And you choose your best point. So here, if I was looking over these points here, this is actually the lowest cost, or equal to the lowest cost of anywhere on this edge, right? So if I finish either of the matrices, the least cost I can incur is 1.5. I can also get it here and here, but here it's like I finished both vectors. And then I can do the traceback, and it gives me the best path. So that's, and it's just, you just have to calculate each cell once, searching over the preceding cells, and you get the entire thing. So here it is for the two versions of Let It Be. This is in beats, so I've done the beat synchronous analysis and then done the, cosine distance between the 12-dimensional chroma vectors. And here's the best path, which you can see is pretty straight. When you look, when you look at this kind of large-scale similarity matrix, you often see, for music, you often see a lot of these stripes here. So a small distance, a small cost is what we're looking for. So we're looking for values which are white. That's the We're trying to find a path that stays as white as possible without getting too twisted. But you see these off diagonal elements, and these are the music aligning with like the verse or the phrase one cycle later. Yeah.
Like if you have the frequency domain, there is the amplitude for each frequency, and for another frequency, suppose you also have the frequency domain. So and the distance is between the difference of the two amplitudes.
Right. So when you're doing this kind of comparison, you get to choose what kind of distance measure you're going to use, right? So the basic question you're trying to ask is, if I've got this little frame of one piece of music and this frame another piece of music, should they align with each other, or are they not a good match? Now, one thing you could do is just take the spectrum, take the waveform, and subtract it. That's going to be very messy, because waveforms, if they're exactly the same, they'll get a small Euclidean distance between them. But even if there's just some slight time misalignment, the Euclidean distance can grow very fast. So unless you've got some reason to believe you've got very good time frame alignment, you don't want to use the waveform. Okay, if we take the spectrum, and then if we take the magnitude spectrum, the spectrogram, then that, because the slight timing differences will land up as phase differences, but they'll still get the same magnitudes. You don't have this problem of having to worry about exact time alignment. So taking FFT magnitude frames and subtracting them, okay, now if they're the same spectrum, they're going to match up well. But if we look at something like the Nick Cave and the Beatles, they're not the same spectrum at all. They're very, very different. So then you can do things like, okay, I'm going to maybe, well, firstly, if you just take the Euclidean distance, then if you just halve the amplitude of one of the waveforms, even though it's exactly the same waveform, it's still a large Euclidean distance. So that's why Euclidean distance you have to use it carefully. If you've normalized each frame, so if you've taken each frame and you've made it so it's got same total energy, then Euclidean distance makes sense. If you haven't got normalized frames, it's a pretty dangerous thing to use. The cosine distance, where we take the inner product and normalize by the total energies, takes care of the normalization, doesn't it? It's invariant to scaling of either vector, because basically you're taking the angle between these two unit vectors. So that's a good thing to do. But it's still, you could do that on the spectrum, or in this case we're doing it on the chroma. So because the point about the chroma is we're trying to strip away the instrumentation information, right? It's just saying, well, there are some notes present, there's some energy in the different semitone bins corresponding to those notes. We don't worry too much about which instruments are causing that, or where the energy is distributed in octave, right? So by taking the cosine distance between chroma bins, which is actually equivalent to some form of the Euclidean distance between it's deterministically related to the Euclidean distance between normalized chroma bins. That gives us our best shot at matching what we think might be different instrumentations of the same piece of music. Okay. So here's the two versions of Let It Be with the Nick Cave time warp to line up with the Beatles, I hope. Hang on, sorry. It's the balance problem again. Let's try that. You can't hear them. Hang on. Let me just play it like this, okay? It's like in balance between the two. So that's actually correctly aligned musically, but it's just because the way Nick Cave sings it, he's singing later, but you can sort of hear what's going on. So that's kind of an interesting effect, and you can use that. I don't know. That obviously is like a trick, but it's been used for things like comparing different performances of piano pieces where you want to be able to play through, and then you want to be able to hear how different performers have interpreted the same piece of music at the same time. So you want to be able to switch between their performances on the fly. Yeah.
So is this done mainly with like musical pieces? So if you had like speeches or something, like no, just relax. If you're using chroma, which obviously just notes.
Right. So you wouldn't use chroma for speech, because also you wouldn't, if it was two people saying the same utterance, the pitches we wouldn't particularly expect to match. What we'd expect to match would be the phonemes, linguistic categories, and then we would want to use a representation that was good for matching that, which is most often is the Mel frequency kestrel coefficients. But you can do that. So instead of having beats and chroma, you have just regular 30 millisecond frames, fixed rate frames, and MFCCs. But then you get the same effect. You can do the alignment and synchronize them, and you can get interesting effects. So basically, you can cause one person's speech to take on the timing of another person's speech, or you can more often. The reason you do that is because you want to compare the exact how those individual voices vary. So this is often used there's this area of technology where you try to map one person's voice to another person's voice. And part of that is, well, they have different vocal tracks, so they just have different formats and different vocal qualities. But so you want to train a model to take the frame of one and convert it to the frame of the other. But you need aligned data to do that. And so you'll get them to read the same. If you have access to the people, you'll get them to read a standard text. Then you'll do the alignment like this. Then you'll have a set of corresponding pairs so you can map from one to the other. And that works pretty well.
Here you are only using the magnitude of the Schopenhauer transform from each to the
I'm using chroma here. So I'm using the 12-bin chroma frames, yeah.
You're using chroma.
Yeah. It wouldn't work. It works better with chroma because that minimizes the distinction between the piano and the guitar. Oops. Yeah, we got that already. Okay. Okay, so that's aligning two audio signals. But we also said there are corresponding problems of trying to align the audio to some kind of symbolic description, like a score or a MIDI thing. A MIDI is, the set of a sequence of synthesizer commands which just say play this note at this time. So it's essentially an electronic score. And so the way we can sort of draw this, just to have something to look at, is so here's the grayscale is the spectrogram of the audio, and then the red boxes. Every time I get a note in my MIDI score, I figure out what frequency that note should be at, and I draw a red box around where that note would occur if it were just a sinusoid, which for musical notes it'll be the fundamental of the note if it's there. I'm trying to see how well that aligns. But so here's the sound example. Let's see if I can get the balance right this time. Okay, so Beatles on one side, and the MIDI on the other side. So the MIDI has so you can do the same thing for aligning an electronic version of the notes, and then of course we've got this advantage, like I said, that you can go in and I can say, well, where was there a particular D5 in the MIDI after I did the time warping, and then I can go back and I can pull the audio frame that has that same note present. How do we do this? Yeah, sorry.
But when you say this is, you can use this to like compare performances or something like that.
Yeah.
Having taken out the time differentials, what would you be
So when I was talking about comparing just performances, it wasn't, you wouldn't do that. You would, I mean, that was like, you could be listening to one performance at a time, but you can switch and start listening to a different performance, you know, at the same point of the music, but you'd hear the actual rendition that the different performers had used. Right? That's one application that I've seen. This idea of synchronization, I mean, it can be useful in when you actually want to. You have two different recordings, and for some reason you want to mix them together. I mean, for sort of doing mashups and like this, it can be artistically interesting to combine these different performances in sync. And then, yeah, if somehow you've got metadata, you've got aligned data with one version, you've got these two different versions, and you want to figure out how to propagate the aligned information, like transcriptions, to the second version, then you want to do the time warping. But really, what you need to get out is just this time warp map, and then you can push your data through that to get your alignments to match up. Okay, so if we've got this problem trying to align audio to score, how do we do that? One thing you can do is simply take the score, the MIDI or whatever, and generate a MIDI version, audio version, and then just treat it as a new performance and just do straight audio matching based on that. And that works okay, but it's a little bit, it's throwing away some of the information you have, because you don't just have the audio, you actually have this higher level information of which notes occur when. And in particular, because the MIDI version will often sound very different from the original, because MIDI instruments are going to sound very different from the original instruments, you get pretty bad spectral matches. So a few years ago, these guys at IRCAM, Oreo and Schwartz, came up with this idea of a way of measuring the similarity between a score and a piece of audio, which is basically this thing. They call it the peak structure distance. And what it is, you've got the spectrum here, x of k, then you've got a mask, m of k, which is derived from the score. And so here's your score, which is, we can display as kind of a set of notes versus time, a piano roll, so-called piano roll, where each black mark indicates a particular key that's being held down on a piano. You've got the score, you can either synthesize this directly to audio, or you can try and predict what the spectrum ought to look like by saying, well, this particular note, which is C3, that has a fundamental of 260 hertz. So, and then I know I'm taking a spectrogram where 260 hertz is the 10th bin or whatever. So I'm going to expect that there should be energy in this 10th bin, and then do the same for all these other notes. You get a set of bins where you expect the energy to be. And then you can take the actual, to compare this score against some audio. This is now your M of k. So for each bin where M of k is 1, you calculate how much energy there was in the audio, in the spectrogram, in those bins, and then you calculate that as a proportion of the total energy in the spectrogram. And that's going to be something that's close to 1 when all the energy is in the bins that have been marked by M, and 0 when the energy is elsewhere. And so we turn that into a distance by taking 1 minus that. And that's what it's saying is that we're measuring how much of the energy in the actual signal is in the bins that we predicted. But we don't care where in those bins it falls. If we just took an actual synthesized thing and then looked at some sort of similarity between the synthesized audio frame and the actual audio frame, it's not just, we expect that the peaks have to be in the same bins. They have to be the same values as well to get a close distance. But here it's like, as long as the energy in the spectrum is somewhere under these masked bins, then we're good. And that allows us to have variations in timbre and in the mix between different instruments, because we're not differentiating between where the energy lies. And that's here. I've just predicted the mask where I'm just looking for the energy in the fundamental of every note that is in the score. Of course, you can go further than that and say, no, I actually expect this note to include energy at the fundamental and harmonics. So you can have a mask of the first 4 or 6 harmonics, something like that, and you can get a pretty good model of where you think the energy is going to occur. Of course, the danger is at some point you start filling in the mask, so most of the bins are 1, and then it starts doing false matches where it's like, well, this mask will match pretty much anything. So there's a little bit of care you have to take in making sure the mask remains sparse, so a random frame won't match very well, but it will pick out the right frames correctly. Okay, so these tools for aligning audio, they've been used in their own right quite a lot for various tasks of synchronizing and propagating metadata. But a more challenging application is this problem of detecting cover songs, where you have different versions of the same piece of music performed by different people, and you might like to be able to pick them out. So this is something that, if you're doing some kind of search for a piece of music, it might be relevant to return as in that search other versions of the same piece of music. But if it's like if the search item is the original piece of music, how do you match that against other performances? And of course, performances can be fairly diverse. So let's listen to some more versions of Let It Be. Here's the original Paul McCartney.
When I find myself in times of trouble, Mother Mary comes to me.
And this is an American Idol performer. Anyone know who it is? I forget what her name is. I mean, it's pretty straight. It's slower than the original, and obviously she's singing an octave higher, but it sounds very similar, but acoustically it's got a lot of differences. Then this is the reggae version. And then Beatallica is a Beatles cover band that manages to mash up each Beatles track with a Metallica track. The pleasure in working on this kind of problem is that you get to hear all these incredible versions. So, how are we going to match these? Well, as we've seen, if it's the same harmonic sequence, then they ought to match. We ought to be able to do this alignment, and if they are the same piece of music, then we expect the alignment to work out pretty well. And if they're unrelated pieces of music, then they're not going to align so well. So we could basically try doing this kind of alignment between every piece of music and then look at what the actual total cost is, right? Because dynamic programming will always find a path. It'll say, well, here it is. This is the lowest cost path. But, the lowest cost might not be very low. So you could just look at the total lowest cost, or you could try and look at the path and see whether it's plausible as being a proper alignment and things like that. But that's the general principle here. One of the things that can happen when you have a cover version is that the new musician will mess with the structure. So the original song may have had intro, verse, chorus, maybe 3 rounds of verse, chorus, and then end. And the cover version may repeat the verse or eliminate the chorus or eliminate the bridge, something like this. So if you try and do the alignment where you want each track to align beginning to end in both versions, that will work in some cases, but there will be other cases where there's no good beginning to end alignment, even though certain subparts do align very well. So there's this variant of dynamic programming called local alignment dynamic programming, and it actually comes out of the genomics world, where it was developed to, if you've got 2 strings of DNA, and they may have the same or related genes in them, related sequences of base pairs, but you don't expect the whole thing to align, and you don't know where they're going to occur. then you can try and do this local alignment dynamic programming, and it'll find little subparts that match. So the basic measure here is still, some kind of best cost to point ij is the max over some set of preceding points of the cost of that preceding point plus the local alignment cost. But the two things that have changed compared to the previous version are we have this pxy, which is basically, well, I guess that's sort of like the transition cost that we had before. But now it's actually used as a kind of a minimum on the local cost. That we want the local cost to be, we're saying local cost is only going to really count if it's larger than pxy. And the whole thing is floored at 0. So if the total cost to this point goes below 0, then it stays at 0, right? So in the normal dynamic programming, the costs are always positive and they always accumulate. Here, we've got this kind of discount term where for every step we're allowing a certain amount of cost. This is no longer cost, this is now score. So it's the other way up. Instead of taking the minimum cost, we're trying to find the maximum score, okay? And so here you have the score you got so far, the new score, which is the local similarities, they want them to be larger. But then you have this sort of penalty, which is the least good score that you can tolerate. And so these things accumulate up, but then if they ever fall below 0, because basically you're not making, your local alignment isn't as good as, your local match isn't as good as your penalty, then it falls to 0. And then basically once it gets to 0, it stays there. So the 0 is kind of the null state. It means like we've got the traceback ends, we didn't find anything interesting, this is starting from scratch. But what this means is if you have some kind of distance matrix here, which is based on this local alignment score, you have these white areas where it's bottomed out. It's said, okay, there's nothing interesting before here. But if you now have some local match that begins to occur, that suddenly start getting Sijs which are larger than the corresponding penalty term, they can begin to build up. And you can say, well, even though back here there's no good match beyond here, we can spot that starting from here there was a region which did match well. And then it might be later on this thing dies out, but you can look over the whole matrix for some point where there was locally a large value in this best score, and that will be at the end or in the middle of some region of good alignment. So I've played with this, and it's been used in a fair amount in audio, and it works. It's been used quite successfully. But the values here are very critical. And in particular, they're kind of domain dependent. That you have to have a penalty term which has the right kind of relationship to the actual values of the local score that you have. Because you want it to be this knife edge between things that, once things begin to be positive, they can rapidly build up because you're going to keep adding them on. And once they become negative, you can rapidly go down to 0 because there are lots and lots of steps here. So you have to get this value just right, and it has to be based on the actual values that you expect to get out of your local match score. But if you do it right, it's able to get around this problem of requiring the entire sequence to match. So you can find these submatching sequences. So the best performing cover song system has been done by it's work done by this guy, Joan Serra, and he was working with Emilio Gomez back in 2008 from Barcelona. And they use local alignment dynamic programming to match candidates to see whether they can match. They do a bunch of other things. They use what they call HPCPs, which are a variant of chroma. So they're taking chroma features, which is the sensible starting point. The first thing they do is they sort of take the average chroma features for the entire track. And they do that for both tracks, and they look at a relative transposition of the two chroma vectors to see at what point they line up the best. So assuming they are the same track, then there's going to be some distribution over notes, and there's going to be some, if they're in the same key, then they're probably going to line up straight up, but it might be the cover version is in a different key, in which case there'll be some shift of the chroma, some rotation of the chroma, that'll make them line up. But they figure out what that is overall, the global, the optimal transposition index. And then what they do is for every frame to build their similarity matrix, for every frame, they take individual, okay, now we've got, for the individual frame, we've got the chroma vectors, and we can do the same thing of like looking for the relative transposition that makes them line up the best. Basically, you try them at every possible shift, rotation, and then you take the inner product, and you keep the one with the largest inner product. And then, so that gives them for every frame, you can get like a matrix of best transposition indices. And then they just convert it into a binary matrix by saying, well, for all the frames where the locally best transposition is the same as the global transposition, then that's a 1, and everything else is 0. And so what's clever here is that they end up with this matrix where matching frames will match, but everything else, even if it's just quite similar but just a little bit different, it becomes 0. And then that allows them to do this, because this gives them and sort of on average, right, if it was just random things, then on average, there's going to be a 1 in 12 chance of the right transposition being, the actual transposition having to be the right one. So it gives them a binary matrix with a well-defined statistic so they can set their Smith and Waterman parameters, and it'll work very well for a wide range of music. That's kind of the subtle thing about what they did, is they managed to get around this problem of having to figure out how to make local alignment scores comparable by converting their similarity matrix into a binary thing, which is like, well, there's got to be some transposition which matches, and is it the one that matches the true or the best guess of the global transposition? So here, this is their binary matrix, as compared to just taking the Euclidean distance between individual frames, which is much more kind of patchy and will depend on the properties of the particular track and stuff like this. And so this is for an aligning piece of two pieces of music that do align, and here's sort of the result from a random decoy, and you see there's no nice diagonal structure you can pick out. What is the piece of music?
Not cover matrix.
What is the?
Not cover matrix.
Oh, it just means like it's comparing one song against a different song, which is not a cover of it, right? So this is, if you take two arbitrary songs and do this comparison, this is what it looks like. You still get a bunch of white spots, right? Because on average, there are going to be some places where the transposition is the right one. In fact, it looks kind of like a little bit. A random you'd expect to be 1 in 12. That seems to be a little bit more, but it depends. If they're in the same key, it may come up more often than that, even if they're not the same melodies. But once we do this dynamic programming, where we're looking for sequences of diagonal sequences which are consistently have good local match, it's going to filter all this out, and we're not going to see any local match coming out here. I also developed a cover system which was based on this idea of correlating individual beat chroma patches from one track and another. So the idea is that, well, here's this actual chroma vector, which is sequence of chroma vectors, which is normalized, and if you look at them visually, you can sort of see these places where they match for cover versions. And so what that would mean is that they would have high correlation. If I take this patch and put it on top of the other track at the right point, calculate their inner product, their correlation, then it would be large if they're similar. You could imagine doing this, but there are a series of problems with it. How big are these patches that you want to extract? You want to you don't want to make them too short, because then they'll just happen to match a lot. You don't want to make them too big, because they might be larger than the matching region. Let me just finish this. And then if we do this for a lot of different patches, we have to combine all of these different scores to get an overall score. And of course, we end up doing a lot of calculation. We're going to calculate a lot of these individual correlations, so the whole thing is expensive. Yeah.
If we run it for chroma, so one set of the features, if we have a soundtrack that have several thousand features, and we have only a sum of them, and we want to find the best match.
Yeah.
The sum to compare to the original one. So,
Right.
I think there will be very time consuming.
Yes.
There's a way for fast searching.
Yes. So, in both in the Sarah and Gomez system and in this system, the underlying idea is we take each track and we compare it against every other track, which means if we have a set of n tracks and we're trying to find all the cover versions in that set of n tracks, we have to make n by n comparisons, n squared comparisons, which grows rapidly with n, and then each of these comparisons can be quite expensive, as we've seen. Even though the dynamic programming is very efficient when you compare it against evaluating every possible path in the exponential set, but it's still, a lot of calculation. And here we're doing all these correlations and somehow combining them. So what we'd like, it's not in the slide pack, but what we'd like is some way of indexing these things where we can take a bunch of tracks, analyze each track once, put it into the index, and then we get a new track. We can break it up. We can query the index, and it'll tell us if we have any tracks that match those.
So like a hash table.
Exactly, like a hash table. A hash table is what you want to do, where you basically have some aspect of what you're looking at, and then you can immediately then that takes you to a particular bin in your database, and you've already filled that bin with all the other items that have that same aspect, and you just read them out. So it scales very well. Assuming, depending on how you build your database, it doesn't get any longer to read that bin as you add more items to it. So actually, this is one of the possible attractions of this approach is that, correlation is kind of expensive, but actually you can view these as queries into some kind of hash table where you sort of quantize these and put everything that's sort of similar in the same hash table and you get it out. But let's just follow this through anyway for now. So the way I got around this problem of how to basically deciding what size patches to use was to not use patches at all, but actually do the cross correlation between the entire tracks. Now this sort of seems like it's going to break that problem of if the patch is too large, then the right alignment for one part of the patch might be different from the right alignment of another part of the patch. So you're not going to get both parts at once. But what's nice is that it turns out that doesn't matter that much. That if you do the correlation, so basically what we're doing is we're taking this entire patch, we're putting it down on top of this, and then doing the pointwise multiplication of every point and summing them up. But then we're shifting it for all possible time skews and repeating the calculation. We're also shifting it for all possible chroma rotations, all possible transpositions, and repeating the calculation. So we get this two-dimensional result, which is the correlation, the inner product between these two matrices at all possible relative timings and at all possible relative transpositions, circular transpositions. And so a darker value means a larger correlation. And you can't see it really in this picture, but there's a fairly distinct dark spot in here which corresponds to the best transposition and best alignment. The reason that it's nice is that you don't have to decide on a length. And what happens is if you've got some little chunk in here which does match, when you do the correlation, the global correlation where they line up, then they correlate and give you a large value. Now let's say everything else doesn't match up. But if they're unrelated, they average out to nothing, right? Depending on how you set it up, you can have it so that they don't contribute because there's so many of them and they're all just kind of random. So what this does is it sort of finds the largest coherent point and sums up over that. And then depending on how good the alignment is, if they're very, very close match and or how long it lasts for, how many points you've got that are lining up this way, then this large point here represents a combination of a measure of the quality and the duration of the match. It turns out that because having a high quality match of any duration is quite unlikely, even if you only match on a tiny part of a relatively short part of the track, that still is enough, usually enough, often enough to distinguish a true cover from a random piece. Here's the cross-correlation matrix again. I've taken a slice through the best row here. And so this is actually just the value of that slice. And you can see here's the sharp spike that you can't see because of the color map here, but it actually has this very, very well-defined point when they line up correctly. Again, we have this problem that we want to be able, that there's going to be some level of correlation between unrelated tracks. And the thing that's really a very strong indication that these tracks match is that the correlation suddenly gets very large and then within a couple of time steps dies away again. And so the one way you can get at that is by simply high-pass filtering this thing a long time, which gives you this. Basically, you remove the slowly varying parts, emphasize the rapidly varying parts, and look for a large amplitude peak in the filtered version. Because cross-correlation is actually just convolution with a time-reversed version, so it's basically a linear filtering operation. Using a high-pass filter in time after you've cross-correlated is the same as doing the cross-correlation on matrices that you've already high-pass filtered. And so another way of understanding what you're doing here is doing a correlation between the high-pass filtered, which is approximately time-differentiated chroma matrices, which is now, rather than trying to match the actual values of the chroma bins, we're trying to match the transitions. So we're looking for places where they both go, they become large or disappear at the same times. And so that gives me a cover song system where I can just simply, again, doing this n-squared comparison, compare every track against every other. So this is like a set of 23 cover pairs that I found in my US pop data set, which has like about 8,700 songs. And so this is one version of each track, and this is the second version. And then the matrix shows the sort of the peak value of that global cross-correlation, high-pass filter global cross-correlation, and the diagonal is matching the true covers. And then the off-diagonal, and the red dot shows you the largest value in each row. So it's of all these tracks, it's the one that is chosen as the cover from these. And you see it gets many of them right in this case. But you can also see there are certain tracks here, we've got these vertical stripes, and that's saying like, for this particular track, a large number of the comparisons gave a large value. And then for this track here, it also got a high score for all the other tracks. So there's some normalization problems that certain tracks just act as good decoys. Yeah.
I was going to ask what properties of the track do you think about striking?
Yes, good question. Sometimes the beat chroma, it depends. So there's a lot that goes on with the normalization here. Right, that if we're just taking the correlation between two matrices, a matrix that has more large values in it will get a larger correlation. It turns out that you could control the energy of the two matrices by dividing by the sum of the squares of all the bins, and then that would be normalized. But that turns out not to be the most effective way to normalize, because basically, if there's a particular chroma bin, it has if it has a lot of values which are about the same, then they all get sort of pushed down, versus if it has one value which is large, then all the energy gets concentrated in that. It turns out that it's better to normalize chroma bins by their maximum value, so that if there's one bin which is large, then it doesn't matter what you add to it, it stays the same, right? You can have just the C alone, or you can have C, E, and G, but the C stays the same. But then if you have, then you get the the beat chroma varying in density, the total energy of these beat chroma matrices will now depend on how many notes there are present. And so you can get certain tracks that have a lot of just more energy in them, and so they give higher correlation values. There's been some work. This is a common problem in these kinds of classification or identification problems. Like speaker identification is a similar problem. You've got maybe a set of speakers that you know about. You've got a sample of a particular voice. You can find the one model, the one known speaker that it matches the most closely, but is it really that speaker or not? And you have this problem of trying to normalize your scores. Often what they do in those kinds of situations is they'll have a cohort of just like a group of average speakers, and they'll look at the similarity across this set of average speakers who are known to be the wrong speakers, but then they'll use that to normalize the scores against the models. So then there's been some work like that done for this as well. Yeah.
Is it possible to introduce the semi-supervised learning to open a website and the user can rate this, the user can give the score for each track and they can classify and okay, this is pop or R&B and for the server they can calculate the data and then to train the machine SVM and then will be a much better
So
model.
there are a couple of ideas in what you're saying there. One is to get user input, right, which is, I would call that an active or interactive or an active learning type framework. So you can have the system say, well, these ones look similar to me, but what do you think? And then if the user says, okay, well, these ones are good and these ones are bad, then you can use that to try and refine what you're doing. And the idea of semi-supervised is that, well, you have a limited number of labels. So you say, well, these ones are, I don't know, there are a couple of things you could label. You could say these ones are true covers, and it could try and find other pairs that have similar properties, and then it would sort of propagate the truthness to those. Yeah, I mean, those are all good ideas. It's one of the interesting problems with this is that there's relatively limited number of. It's not that easy to find these, right? So come up with these 23 covers. What I did was I had this database of 8,700 songs. I sorted them by song title, and then and that gave me like several hundred pairs or sets which had the same title. And then I had to listen to them, right, one at a time, to decide whether they were covers, because I didn't know many of these songs. And that was kind of interesting because sometimes it would be like, obviously this is the same song, or obviously this is a different song. And sometimes it would be like, I don't know if this is the same song. There are some similarities here, and right, and because if it was a song I didn't know, I would have to listen to quite a lot of the original song and then quite a lot of the cover song to say. And very often, actually, the thing that was the final factor was that the lyrics were the same, right? That if they have lyrics and the lyrics are, you can tell within a sort of couple of lines whether the lyrics are the same. If they're actually real verses, you can tell if they're the same. But at the moment, the cover systems aren't able to transcribe lyrics, and so we're not using that cue at all. But as a result, I only got 23 of these out. In the end, I found some albums of covers and added another set. So I have my personal set of 80 covers, but that's very small. Since then, we've been able to. There are some websites where they collect cover songs. There's this website called Secondhand Songs, which is. Sorry.
Yeah, music also do that.
Oh yeah.
Competition is about they have a lot of research.
Right, sure.
The scores and ratings.
Yeah. But we're particularly, if you're particularly trying to find two performers of the same song, we've gotten a lot more data since then. Okay. This idea of doing this global correlation, you can actually break down. You've got the total correlation score, which is the spot in the middle of the matrix. It's the sum of the point-wise product of the beat chroma matrix 1 and beat chroma matrix 2. You can break this down so you can do the summation across frequency first, and that gives you this kind of like component correlation contributions as a function of time, which is shown in cyan here. And you can smooth that, and you get you can see where there are local regions where there's a lot of contribution. This is for the Let It Be versions. There's this big peak here, which is the kind of the da-da-da-da cadence which is well preserved between the two, and that gives you a large contribution. In fact, this is the bit in the middle where they do that over, they switch to the organ. So, but this gives you some insight into what's matching and what isn't matching. This is a false alarm. It matched Satisfaction by the Rolling Stones to Cocaine by Eric Clapton. And you can sort of see what's going on there if you look for these regions of large correlation. It's just like this. Both of these tracks, let me just play them to you in case you've forgotten. They have sort of a fairly short and fairly simple riff. And that's Eric Clapton right. So those two things actually match, and they're not cover versions, right? But it's just that it just happens that there's not a lot of other structure in the song, and those things are sufficiently similar to end up matching each other. Okay, so we don't have any time left, but let me just quickly tell you what's going to happen on Wednesday. We're going to be looking at trying to do some matching between large music databases, and we're going to be using this analyze service from the Econest. The Econest is this startup that does kind of music information. They do a range of different things, and it was started by a guy who was at one point was a student here, and it's an interesting, exciting thing, and they do a bunch of different things, including letting you upload a piece of music, and they'll give you the chroma analysis and other things back. So I've written some MATLAB wrappers which let you upload an audio track and get back their analysis. But we've also, and we'll try with that, but one of the things we did this year was we put together this million-song data set. And what it is we basically worked with the Econest to get their analysis output for 1 million popular music tracks. And this is now a data set that we distribute. So we're not going to be able to work on the full set because it's like 300 gigabytes. But we're going to play with a small subset of that on Wednesday and try and find some matching at different parts. So I guess I'll tell you more about that on Wednesday, but that's something you can look at you can have a quick look at what's coming up on the website. Okay, so in summary, we talked about music alignment by dynamic programming. We talked about cover songs using dynamic programming, or this cross-correlation, which gives you some opportunities for efficiency. And then I just quickly mentioned the Econest Analyze. Any questions? All right, I'll see you on Wednesday.